Hello all. As my colleague Yama said, my name is Martin Brestovic, and I'd like to share with you some, let's say, some details and some technical aspects which we shouldn't forget about at PCB design. Naturally, we don't have aim to say everything. As you know, it's impossible to say all about PCB design in 1 or 1.5 hours. But there are some aspects which you really shouldn't forget about, and it's very possible and very probable that many of them you will be familiar with, which I will talk about, but hopefully at least something you will find new or interesting, or maybe something what you didn't know about so far. So this is our aim. Our main, so to say, material which we are coming from comes from Department of Technologies and Electronics, Faculty of Electrical Engineering and Informatics, Technical University of Košice, Slovakia, as you can see on the bottom of the page in our presentation. So let's start. In the beginning of electronics, as you probably know, there were no PCBs, and there were only wire lead connections, and PCBs looked more like some network, and not something which has some order and not very nice at the side. And of course, from electrical point of view, it was very hard to ensure some consistent production, and manual demands were very high, what also made products quite expensive. That's why as soon as first PCBs arrived on market in 1957, there was founded the IPC organization, or this Institute of Printed Circuits. Almost everybody in the beginning who became member of this organization, so to say, accepted some basic rules, and he declared that he uses some standards which became to mutual acceptance, and which made all production of electronic much more consistent and much more effective. In the 1999, the IPC shortcut or abbreviation has simply changed into Institute for Interconnecting and Packaging of Electronic Circuits. Nowadays, the IPC has about 2,700 members from all over the world. I would also say that in this presentation, maybe you will find I will something overcome or skip. My aim is not to read or tell you everything what is here written, because all this presentation you can then see also from our webinar web page within a few days, as soon as we will upload it to server. But I will try to focus especially on some maybe details or something what I personally consider as more important. So as for PCB design and recommendations, we can divide it into these basic segments. First is way of component soldering. Second is technological possibilities of PCB production. Then electrical functionality of a device, and so to say, in practice, the proof that our PCB design was successful. And at last, PCB design and electromagnetic compatibility, what becomes still more important in the nowadays very dense electronics. Soldering of components, probably every electrician knows basic components, so only in short, we have through-hole, we have SMT, and SMT we can divide into devices with pins, or yes, at least very short leads, and SMT devices which have no leads. Devices which have at least short leads can be soldered by a wave or in reflow oven, and SMT devices which have no leads can only be soldered by in reflow oven by placing into solder paste. Probably only more experienced or maybe older of you know a solder wave. It is showed on the bottom of this picture. There is simply a solder bath heated on melting temperature with some additives, and the PCB is moving towards the wave of the solder. The solder is really agitated from the bottom, so it creates a wave, something like a wave on water, and as the solder touches the PCB from the bottom, the components are being soldered. It was mainly from the beginning of electronics, and still nowadays it is used, but it is mainly suitable only for THT components. So for through-hole it is almost the only solution, but it's not very suitable for SMT components. SMT components can also be soldered this way, but they have to be glued to the PCB because in other case they would be flushed away from the PCB. So when you look here at this slide, just excuse us because of some Slovak description of the pictures, but I think it is quite clear. In point A, we have a classic THT design. Only THT components are used, and they are only from one side. So the PCB is single-sided, everything is soldered from the bottom side. On picture B, we have a mixed, or no mixed, only SMT montage, and it is also only from one side. It is also quite simple case. On picture C, we have already a more complex case. It is a mixed design. THT are from the top, or also SMT components are also from top and also on the bottom. On picture D, we have only SMT on both sides, and on picture E, it is THT up, SMT down. We can say all these cases are quite usual in electronic practice, but nowadays I would say maybe the most frequently used version is C, so it is the most complex, where SMT components are from both sides, and in a little bit only small, bigger or other components which are not available in SMT packages are mounted manually, for example, into THT technology. So As you know, when you want to solder in a reflow oven or on solder paste, there is a solder paste placed on a PCB. It is really something like a paste. It has such a consistency, and simply all SMT components are placed into this paste. They are held by simple gluing, something like gluing by this paste, as it is quite sticky. So the components hold already on their places, and when the board is populated by components, it is put into reflow oven. There is some preheat time, main soldering time, and then cooling section. So by this procedure, which lasts few minutes, all components are soldered usually in very high quality, without any tension or misproperties, and according to all recommendations by producer of components. Usually the heat profile is selected according to the most sensitive component, which is usually some of integrated circuits, but also sometimes some special high-frequency components, filters, and similar. However, there are still cases when the wave soldering is unavoidable, or simply it is good from, for example, economical reasons. In this case, still, if you want to use mixed production PHT and SMT components on one board, for example, still you should keep in mind that all components which go to oven or to wave should be placed perpendicularly or in the right angle to the wave. This means, like on the left picture, when the PCB comes into wave, the wave of the solder becomes or flows through all components, and it simply has, at the last pin of the component, it has to go away. When the component is big enough, it is no problem for the solder to leave the component. But when the components are quite dense, it means they have a low pitch, like at integrated circuits. It is often quite problematic for the wave to leave components without bridging or making shortcuts at the last pins. It is illustrated on the right picture, and it becomes quite a problem at these situations. But we can avoid it by placing so-called rubber pads, or simply there are additional pads with no electrical connection, and the only purpose is to take the solder away from the last pin, or from last two pins, to avoid making shortcuts. On the other side, when we solder SMT components, we also have to keep some rules when soldering by wave, and the main limitation is that the pads have to be quite bigger than minimum used or minimally required sizes, because simply the solder has to catch at some surface. You usually you can't use the size of pads which are easily used at reflow soldering, because at wave soldering you need simply bigger pads for the solder to be able to catch. Still, it is used, and as I have said, mainly at mixed design, where there are a lot of THT components and manual soldering would be inefficient. So in that case, there is usually SMT component glued to the board, and all this is put into the wave. Still, even the quad integrated circuits, which have pins on all sides, still even they can be soldered by wave, but in this case you should place integrated circuit in 45-degree angle so that the integrated circuit would come into wave in this angle, and to leave this wave by something like prolonged pins, these rubber pins or rubber pads, which will also take away the excess of solder. On another side, you will almost certainly get some bridges. Of course, bridges and shortcuts in general are also affected by type of solder, type of flux used. Yes, PCB soldering companies have much more experience in this area, but this is something like a general rule. Now we have here SMT component soldering, which we can say is nowadays the most frequently used method of soldering, and it is simply, as we mentioned a while ago, all these cases when all components are put on a PCB onto a paste, and as the paste is quite sticky, the components hold there. The PCB goes into the oven, and when the paste melts, the micro particles of a solder join together, and they create one uniform solder, and also the paste contains flux and other additives for better wetting, for avoiding bridges, icing, and so on. So nowadays it is a very well checked and well proven process, and still the producers of solder paste also always come with some novelties, with better properties and better practical features for practical use. What is maybe the main unwanted effect called tombstoning? It is the effect when the solder paste simply doesn't have quite good sticky properties, or simply one portion of a two-pin component becomes sooner hot, and in a very short moment, when one pin of a component becomes soldered, there are capillary forces which have quite high force, and they are simply very easily able to hold up the component, something like a tombstone. That's why it is also called this way. And sometimes it is very hard to avoid. Sometimes the solder paste has a very high influence on it. Also, when the components are, for example, older and there is some oxidized layer on the components, this also can cause poor wetting and tombstoning at the end as the result. But also the companies which are focused on this production have usually it very well made and very well checked, so it's not, so to say, extreme danger on everyday practice. What we can say about technological possibilities of PCB production? This way we get to, so to say, the main properties of PCB design, and this is something what you should all be familiar with, or you should know already from the very beginning of the PCB design. In other words, when you start designing any PCB, you know how demanding is the PCB, you know how high frequency signals you process, or for example how dense you want to make the PCB, whether you can allow to yourself some bigger PCB, or you are pushed to make the device as small as possible, and that's why to place components as near to each other as possible. So at least at the very beginning of the design, you should at least know, or at least to check at the PCB producer which are his real capabilities. And nowadays, usual capabilities are, let's say, track width about 0.1 millimeter, the same isolation gap, and also a very important parameter is the minimum diameter of a via. It is something like metal plated opening. So when you know all these parameters, you can, for example, type it into your CAD system, and your CAD designing system, no matter whether it is Protel, Eagle, and so on, it will check and always control whether you keep this at your design, and it will give you some warning in case you would go closer than allowed. For all these cases, it's also advisable not to go to technical limits, because from one point of view, usually these boards are slightly more expensive, which are on the very edge of the technological properties or possibilities, and also even in the case when the producer declares that he is able, and he is really able to make such a PCB, there is still some, even though very small, but still existing risk that the thinner tracks you have and the smaller isolation gaps, there can simply occur some mistake or some impropriety on the PCB, and even in cases when electrical check of the PCB is okay, there can be some, so to say, thin layers or some places which are not 100% okay, and they can show later. So it's always advisable, if possible, to make something like a reasonable compromise between the technological possibilities and between your real demands. In some area, or in some also time period, there were called something like level of accuracy or accuracy class. Nowadays it's not that much used, but you will simply find what is possible on web pages of any producer. Just for a short show, I would show you one producer from Slovakia and what are his capabilities about PCB production. Yes, now we see it is SQP International, but in general this applies to all PCB producers, and here are, for example, some basic declared properties. Production standards according to IPC standard A600+2. Number of PCB layers 1 to 12 layers. Minimum track and gap size 0.1 mm. Drilling, minimum drill 0.2 mm. It means plated through hole will become 0.15 mm. Solder mask, various colors, silk screen, surface treatment. Surface treatment is, as you may know, very important, as bare copper board gets quite fast oxidized. So usually every board which you buy from a PCB producer has some surface treatment. The most frequently lead-free hull, or it means hot air leveling, or simply soldered in a very thin layer across all the board. Also, it can be SNPB hull for application where it is still allowed, and maybe the most advisable is chemical gold. The chemical gold is very durable, smooth and glossy surface, which also is very good for SMT paste dispensing. So it is probably the most advisable solution. Then we have here mechanical finish, various methods of testing PCB boards, and also some further options like carbon layer, edge plating. Some printed circuit boards producers also offer, for example, flexible boards or mixed, like two rigid boards connected with one short flexible board between them, for example. So all these cases depend on the PCB producer. It is simply good to know that there are such possibilities. Yes, so let's go back to our presentation. And this is technological possibilities of PCB production. As you can see here, we have a preview from something like a screen from a PCB design CAD system from Protel. This is, for example, but it doesn't matter. Simply just to demonstrate that, as you may know, every PCB software allows to type in your basic demands or basic possibilities of a PCB producer, and the system will simply not allow you to use something out of tolerance, or at least it will check it when you manually press the manual control, and as a result you will get a board which you don't have to check by your eye or what to say. Yes, it is also not possible in nowadays very dense boards. So a very useful tool nowadays already found in almost every CAD software. Also, you can choose some preferred for example, track width, which the system will offer you as something like standard. Now we get into more, maybe more interesting and more in detail, practical shows what to use and what to avoid at PCB design and at placing components. These are things which maybe some of you know, and maybe there are some details which a designer will experience only when one time some problem will occur. And these are the very nice examples where problems can occur when you didn't work with it so far. For example, on the left image you can see a good design. The first, let's say, resistor is placed, it has its own path, the conductive tracks and the plated through hole are far enough from the components, so the solder mask can go where it should. It will simply stop solder to flow behind the solder pad, and the component is soldered properly without any risk that it will be moved by, for example, by capillary forces away. Also, the third resistor from the left image, when you already don't have any other possibility and you have to place the pad directly on track, it is usually better to make the incoming tracks slightly thinner, just to avoid going away too much solder, and mainly to keep something like balance of capillary forces at reflowing, because everybody who ever experienced this, in every time when you have one pad significantly bigger than the second one, it is a very high risk of tombstoning or simply moving the component out of position, because the capillary forces of melted paste are very high. It is very similar like at water, you know, when you give something to flow over the water, something very light, very lightweight, it will flow, but any near component which is very near will simply pull it or attract it one to each other. And the same forces, but much bigger, are at the melted solder paste. In contrary, on the right image we have examples of poor design. It is all what I've been talking about a while ago, and extra we have here a case of plated through hole placed just at the component, and here is a very high risk that the solder paste will flow into solder, into via, and it will be simply missing on the pad. There will be not enough solder paste on the pad itself. Many designers also are faced by a question: how big current can it go through a track, or how high voltage can I use between those two tracks? As you know, as PCB tracks are flat, they are simply like flat wires and glued to a PCB base, the current carrying capability is much higher than the one wire in the air itself. There are some values, for example, up to 850 amperes per millimeter squared it is able to withstand, but for a continuous current it is it is advised not to use more than 100 amperes per millimeter squared. But these are still quite high values. For praxis, it is used not to excess 125 degrees for FR4 base material of PCB. And for example, on the web, you can easily find many PCB calculators which will tell you exactly how much you should use for a given track width, or how wide track you need for a given current. The same applies to voltage. For example, isolation gap of 0.5 millimeter has a breakthrough voltage of 850 volts. But of course, this is already breakthrough voltage. The maximum recommended voltage is roughly half of the breakthrough voltage, but still you can see it is quite high. Already 1.5 millimeter is able to withstand almost 400 voltage as in usual operation, so it is quite high. But of course, these are maximum values recommended for your, so to say, safe sleeping. It's still better to use bigger isolation gaps, mainly because in praxis there can avoid some humidity, some dust after some time of usage, many impurities which can decrease the isolation capability of a PCB, and in worst case it can go to breakthrough. Also good to mention that a solder mask is something that also helps to increase breakthrough voltage, so every time when you can use it, it is advisable to use solder mask. And as a second step, very good protection also offers usual PCB conformal wax or agents. You know, there are many emails in spray, for example, in spray or in a can. For example, in our offer from Contact Chemie, there are at least 2 types of such coatings which can be used for this purpose, and they when applied after soldering, they also will cover the soldered places, so they simply offer a protection for the whole board. Yes. So electrical functionality and possibility of testing. You know, everybody who ever made anything electrical knows that to design something, to solder something is one step, and the second step is to make it working. And especially at development and at first stages, it's usually quite demanding for testing, for measuring. So there is still good to have a possibility to measure it on one side easily, and on the other side also without damage for components. So, for example, you can see on these pictures correct and incorrect PCB design. On the left picture, you see a case when there is a very small pad near or under the SMT component, and there is virtually no place or no room for some testing probe. You are forced to use testing probe directly on a SMT component. What of course it's possible and usable in practice, but it's not very good, and in some cases it can cause damage to a component. So much better is the case to leave some place for testing near or next to the component, whether it is small resistor or some integrated circuit. Still, some testing points are very good when they are there. Also, for example, minimum distances. Anytime you design a PCB for one prototype, you can solder it usually manually, even though it would look or it would be anyhow demanding. But for mass production, you simply must respect demands of soldering or placing, pick and place machine. Yes, there are some minimum requirements for distances between components. Also, from mechanical point of view, for soldering point of view, for electrical point of view. So even there are all these aspects which you should keep in mind, and as maybe in many other segments of life, usually it's advisable not to go to limits, not to go absolutely totally close one component to each other, and to leave no distances, because also in case you are forced to solder there manually and you simply can't get there by a soldering tool, it's probably never a good experience. When we talk about components and SMT components, maybe we even didn't realize it usually in practice, but the component package and its recommended size and recommended soldering paths are also in some way standardized. And for example, here it is IPC 7351B standard, which says many about standard packages and, for example, about rules for design of new packages. So even when you design yourself some new package or some shape of paths on your PCB which are non-standard, it's still good and always good to somehow to keep it or to maintain it, because these recommendations are not because to make you some rule or some order, but it is something what comes or results from practice, what is good for real practical usage. When we talk about PCB design, now we come to, so to say, third step, and it is the PCB design when you are in a CAD software. No matter which CAD software you have, you go through some workflow, which usually starts with drawing a schematic, then to marking or annotating of components, and then to electrical check, theoretical electrical check. Usually you go through this workflow which is illustrated here. On the bottom side of every block you have English annotation, as you can see. So you go through all these steps, and you simply find that, for example, you are here on placing components. You go through all steps, and it is a very typical case that you have a complete schematic, you are satisfied with how it looks, you know approximately where which component should be, and you are starting placing components. Many design softwares have automatic placing components. As far as I know, very few designers really use it because to leave all placing of components and then routing to some automatic process, it will hardly deliver you some good results, because there are so many aspects that the software simply can't be aware of all aspects which you want to maintain and to keep. So at least on the beginning, you should place some most important components from your side. Yes, so let's say power block, then some, for example, main microcontroller, and then some, for example, communication interface, and something what has very high demands, for example, high-speed components which require, for example, very short leads and so on. So when you root all your board, you usually come into question whether it will be electromagnetically compatible. To root the board, you probably know very well it is possible in many ways. Probably if we gave the same demand for two experienced designers, the result would surely not be the same boards. In both cases, the boards can be okay, can be electrically very good, but simply they will look differently and the components will be placed differently. But what I want to say, that it is your choice, yes, of course, or the preference of every designer. But what every designer should keep in mind, that in nowadays world, when there are still more electronic devices and also very low current devices are often used. On one hand, they produce less electromagnetic smoke, and also on the other hand, they are more susceptible to electromagnetic interference. So, you know, when you use component which uses high currents and which is relatively slow, it simply doesn't care about other components. It lives its own life, and you can hardly interfere it without using some extremely high current. But when you design a low power device with very sensitive devices, you simply have to maintain and to keep some recommendations. One, not to produce EMI, and also not to be EMI or ESD susceptible. Yes, EMI and ESD, of course, it's not the same. EMI is electromagnetic interference, and it can go from almost anything, at least, for example, from your mobile phone. ESD is usually electrostatic discharge caused by direct touch, usually by people, by operator, at a direct touch to device. But in all cases, usually the main goal is to keep the tracks as short as possible, and to use, for example, filtration, to use shielding, to minimize currents in electronic circuits. We will go through it in following steps. So step one, we can say Component placing and PCB design. Naturally, we try to place very sensitive components on one side of a PCB and high current and, for example, power stages on the other side of a PCB. It is by physical separation. Also, for example, we can use more multi-layer PCB, for example, to separate components on the bottom side and from on the rear side by a ground plane. We can see it on these pictures on the bottom, but of course they are something like to show. Yes, for example, low frequency circuits, input-output circuits, and then connector on the very edge of the board. But in real life, we usually meet much harder requirements, and for example, very many components have to be grounded. Yes, ground or common potential simply goes to many components, and you are faced how to ground them without making very many tracks, or without, for example, by using as small place as possible, and so on and so on. So we in practice can differentiate three cases: A, B, and C. A is the most simple one. Simply at least these three components are in something like a chain, where their grounds are connected one to each other and then grounded into one point. Then we have B. We have three different components grounded into one point. This is usually very good type of grounding. And C, it is the case when we have three components, but we have so-called multi-point grounding, and this is usually used on multi-layer PCBs, where, for example, there is a ground plane on the bottom side or in one of some middle layers. This is also very good grounding usually. Case A is the worst one, still usable, but you should use it only at lower frequency devices, and also in devices which are not very sensitive to some noises. Yes, surely not recommended for some preamplifiers or some input stages of measuring devices and so on. Inductances L1, L2, and L3. You may ask what it is when you don't have any inductor used in your device. Yes, of course, anybody probably knows that even the shortest track of a PCB is, in fact, it has some electrical properties. It has a capacity between each other, between two tracks, and it has its inductance. It is unavoidable, and only the length and the size and the surface which makes these tracks defines the final inductance. But in general, it's unavoidable. The only thing we can make with it is to decrease it by proper design. For example, now we can see a multi-point grounding, and it is very nice and very frequently used way of grounding in nowadays, because, for example, at least double layer boards are not very expensive. They are very common, and almost in every design you can simply afford it. In this case, when you use ground plane or bottom side as a ground plane only, for example, sometimes divided by some necessary connections, but we can say it is a one continuous ground layer. In all these cases, you can simply place all grounds to that ground plane. Of course, when we talk about, for example, high current switch to power supplies, in that cases it is good to divide that ground plane into power ground plane and into signal ground plane, and just then to connect in one point. But these are special cases. In general, we can say using one ground plane in two or multi-layer boards, it is a very good solution how to avoid many problems in practice. Because even in the case when you have a good working device on your table and you are satisfied with it, how it works, in practice it can easily happen that when you place it somewhere into industrial environment with a high level of interference, your device simply doesn't have to work. It can fail because it has a very low immunity against such disturbances. So to say, how to be on the safer side, it is quite cheap and good solution to use ground plane as frequently as possible. PCB design and electromagnetic compatibility, power decoupling. The second way or second requirement which usually a designer has to meet and which has to incorporate into his design is to use decoupling or filtering capacitors. For example, we have here such an example. We have CMOS gate with power consumption of 15 milliamperes, which takes for only 3.5 nanoseconds. We have some delay on a PCB which is 0.1 nanosecond per centimeter, and a reaction time of a usual regulator is 1 microsecond. We can see it is roughly 1,000 times slower. The regulator is simply in no case able to cover the higher demand for current, and that's why voltage in such a short time. That's why it's unavoidable to use good quality capacitors, which serve in this case like energy storage. When we look at capacitors, which belong to, even though very simple, but we can say one of the most important things for real usage of devices. We can differentiate them into three types. Filtering capacitors or bypassing serve as a wideband filter for power supply of a whole PCB or its part. It eliminates influence of power supply leads, inductance, and also eliminates for example, low current capabilities from your source. Yes, when you have a device which only for some milliseconds needs high current, you don't need to use high current power source, but you need to cover it by good enough and big enough capacitor. Then local or decoupling. capacitors. They serve as local energy sources for components, and they also reduce pulse currents. They will go through a whole PCB. These capacitors must have some high frequency properties, and it's necessary to place them as near as possible to a component pin. I would say, when you have heard it reduces pulse currents, that would go through a whole PCB. It is a very important sentence. All currents which would go through a whole PCB create electromagnetic peaks, which on one side can have influence on other components, and they also create electromagnetic radiation. And this can be, for example, the cause why your device will not go successfully through certification, for example. And then there are group or block capacitors. They serve as energy source, something like local energy source, but with a higher capacity, let's say 10 or 100 microfarads, for example, near a microprocessor. It doesn't serve for extremely high peaks, like, for example, ceramic capacitors, but they are quite near and they are quite big to solve something like between filtering and between local decoupling capacitors. We can see here some picture for illustration. Of course, in practice, there are concrete devices or concrete situation, but I would say also that what is very important, and many designers from my experience doesn't care good enough about it, and it is impedance of the capacitor. When you place even 10,000 microfarad capacitor on your power supply stage, you can't say you have good filtering and good power source for your device. You need, usually to every, for example, electrolytic capacitor, you need to add your local very good capacitor, for example, ceramic capacitor with extremely low impedance, which is able to deliver power peaks even for very fast devices. And also, very good rule is to use, for example, to your microprocessor, electrolytic capacitor, and also decoupling ceramic capacitor, because this way you can avoid many extremely hard to find problems which simply result in very short voltage dropout. Now we have here now very practical image which shows you how to and how not to connect capacitors in your PCB. On left picture or on the bottom you have correct, on the upper one it's incorrect. As I mentioned, the goal or the aim is always to minimize track's impedance, not only in its length, but as you know, inductance of any two wires depends on their length and on the surface which is between them. So it is extremely important to draw your power lines as close to each other as possible. It's not a good idea to, as it is usually shown in schematics, to keep VCC, for example, on the upper side of your board and the ground on the bottom side of your board. It is nice, it is comprehensive, it is easy to determine on which side you are, but it creates the biggest possible inductance. It makes much more radiation, and it also slows your system and makes it more susceptible for outer radiation, for example. So, like these two pictures show, in both cases you have unavoidable inductances, but with very short tracks to capacitor, you will almost eliminate inductors L5 and L6, and by lower surface between the tracks you will decrease inductances L1 to L4. This minimizing of track width and surfaces in general also applies to components. So, for example, it's good to try to use short tracks. It's good to use or to switch in one moment as small amount of gates, logical gates in digital circuit as possible. Also, to choose suitable logic for your device. In many cases, it's not a good idea to use extremely high-speed logic components. Maybe it's good according to data sheets and to maybe future spreading of your device or capabilities, but many times extremely high-speed logic gates need very short and very high rise and quite fast fall edges, and besides you can get some unstable system. These extreme current courses also can generate many problems, as long as you don't keep in mind all decoupling advices. So, to minimize current loops surfaces, it's good to use, for example, SMT components. They are, of course, much smaller than THT components. Also, in practice, very good components are those ones, when we talk about THT, which have power supply pins on one opposite sides, but close to each other. In that case, you can use small decoupling capacitors right beneath the component, and you can also avoid many problems by this way. Also, don't use sockets at very fast circuits, because it creates more space, and also some microvolts occur on the sockets, so it's a possible source of another problem. Digital circuits. This is already a little bit a special case for those of you who use, for example, high-speed or USB circuit, for example, with USB 2.0 interface, where you always should keep, for example, input-output tracks very close to each other to make impedance matching, or you simply have to design this strip line which has some defined impedance. All of this can be found on web. Also, for various materials, you can find online calculators how to design, for example, 50 ohm exactly matched strip line to bring it through all your PCB, for example. But in all these cases, many times there are used methods called, for example, via stitching or via shielding, where ground planes are on the top and on the bottom, and they are connected by plated through holes, and they create something like a channel, something like ground channel with one track inside it. And besides, it has defined properties. It also makes good shielding, which decreases radiation outside. Yes, one thing to mention, on the right picture, on the right bottom, you can see exactly that case which I was talking about some minute ago. VCC and ground should always be taken or drawn in parallel, not on one from up, one from bottom side, because it creates a very high surface and very high inductance. Now we come into PCBs and something like basic PCB principles and what you can use and what maybe not. Double-sided as probably the cheapest, usually nowadays used PCB if we eliminate one side, even though one side has still a lot of good properties, of course, but two-sided has one very, very high advantage, very big, that you simply can route it much more easily, and usually you can avoid any jumpers, yes, or wire links when you are using double-sided boards. So it's very advisable to use such kind of board. Now, for example, when you see here cross-section, you can see here a plated through hole. You can go from on the top side. Now when you come into component on your way, you simply can give that signal, place it on the bottom line, then go on and go back to top side. Yes, usually very well-known things. When we come into multi-layer, here becomes or starts quite different world, and multi-layer boards, of course, it's a chapter of its own. It's impossible to say very much in such a short time, but just to mention, you can use inner layers for many various ways. At least for grounding, it's very good to use for example, for power supply. Power supply and grounding in two separate layers. You take it in the so-called inside of your board, and it simply doesn't interfere you at your PCB design. Suddenly you have a much easier design when you can use a 4-layer board, and you can afford to use ground and VCC inside your board, for example. There is some layer stack up, yes, all of this can be found on the internet. There are many possible ways of layer stack up, but usually there are some thicker boards and then very short or very thin boards called prepreg. And very fast way to create a, so to say, prototype board is production by a dry wave. Dry wave is not so very well known method maybe for many designers, but simply one specified machine specially designed for this purpose, which is able to use usual drills and also milling drills and milling bits, can simply grind out or mill out unwanted copper layer, and within really few minutes you can get a ready-to-use board. Your board from on your table, and all that is necessary is to have an output file, usually ODB++ or Gerber, Excel, and so on from your CAD software. You will load this into software, which usually comes with machine like this on the picture. For example, this concrete is LPKF, and it is extremely capable machine with a minimum spacing of 2 microns, so 0.1 millimeters. It is simply really comparable to a way or to a method of chemical etching. And what is very good, for example, you don't create chemical waste by this method, and of course mainly you have it on your table, and especially for prototyping it is extremely useful. For example, this concrete type has a repeatability of 1,000 of millimeter. Milling spindle can rotate up to 60,000 rotations per minute. It has automatic tool exchange. This is extremely useful because in real production you need to use several tools, and you simply don't have to stand at the machine and wait until it's signaled to exchange the tool. This concrete machine will exchange it itself, and they simply have to be put into a holder, and the machine will exchange it itself. Many types of bits, drilling and milling bits are used. Basic types are those which have slightly conical shape and those which have a flat, and they are so-called end mill. As we can see on these pictures, one of them makes a line or a groove in a slight shape into letter V, and when using such a tool, very important is also to define the depth of ingress or into engraving into the material. The more you allow it to go to material, to base material, the wider track it will make, yes, or the isolation track. On the opposite side, the flat mill or end mill is fully cylindrical, so it makes the gap which is still uniform, no matter how deep it is set to go into the base material. Now you can see some pictures from real life from such a device, and simply on the first tab you load your data from your CAD software, you select necessary tools, and you place them into holder, which is dead in the middle of the bottom picture. We will see it soon also in more detail. Yes, on the beginning of the process you see which tools are to be used. You define some basic parameters. You define on which position in a tool holder is which tool used or placed, and in general the process of production can start. What is also good, so these machines nowadays usually have a camera by which you can check during or after the process the real distances or the real situation on your board. You can measure distances, you can measure isolation, and for example, in case you are using conical tools, you can, for example, adjust depth of ingress to increase isolation gaps if you are not satisfied. As you can see on this really microscopic or almost microscopic pictures, the lines are relatively very nice and the edges are sharp. So the machine is really capable of delivering very good results. Here we see a look into the holder of your of tools, and yes, now you can see a video how it changes the tools. What maybe isn't visible or obvious at first sight, the tool holder is a little bit slanted, what defines depth of ingress of a given tool. So, according to desired depth of ingress of a given tool, there you place the tool into that position on the very beginning. On the other video, we will see some start of, let's say, outline drilling or milling. On the first sight, it looks maybe like if it was a photo plotter, but of course the difference is it's not something drawn on your PCB, but it is the copper material which is taken away. Here we can also see there is no dust or copper material, some particles or so. Of course, it is because the machine has connection to vacuum cleaner, so all these particles which also might cause problems at making extremely precise lines are taken immediately away. So when you take the board out of the machine, you literally take it almost fully clean, and the only thing you have to do with it is maybe to wipe it with a soft dry cloth and to apply some soldering protective layer. Now we have it also with the sound. I will. Yes, now I don't see a possibility to decrease the sound, so I will let you go all the video and then I will go on with my speech. Yes, so here we have seen some milling of practically away all the board. These were outline borders of the whole board. So after this process, the board can be taken out of the panel, and we get a final board. In practical usage, the machine is closed behind acrylic glass cover. This is the video from the producer. In real life, you are not allowed, for example, to use the machine at the open up deck or front deck. Yes, this was the last video which I wanted to show you, but I will also like to show you some simplified process from etching on the web of the PCB producer, and it is I will just show it to you in a second. Yes, when we come here into SQT International, I will try to find the video. The video presentation. How they are manufacturing PCB board. Yes, here we could have seen something like what's called PCB cutout, and maybe it's a good info for those of you who who aren't very experienced at PCBs so far. When you place order into for any experienced PCB producer, so in the majority of cases, he will also provide you a so-called PCB cutout, what is simply a microsection of PCB. Usually in two or multi-layer boards, it's very good to see it, and it is also something like approval for you that the board has such a spec up which you want it to, and also a confirmation from your PCB producer that he kept the, for example, inner thickness and thickness between layers, for example. Yes, so this is probably all from this website, which I wanted to show you. If we come back to our presentation, this was practically the last slide from our main presentation. Of course, it can't be said everything in such a short time, but we were trying to tell you at least the most important things from our point of view. If you have any questions, we or our external partner, Mr. Livovsky, which I will show you on the last slide, his email from Technical University of Košice. You can write to us on our general address or into this address to Mr. Livovsky, and he will be glad to answer you any technical question which you may want to answer. I will look whether we have here some questions for now. No, so there are no questions for now. So I just have to thank you for your attention and for your time you spent with us, and hopefully it was useful for you, and welcome to our next webinars. I will give you, yes, I just wanted to show you about some future webinars, but you will be informed by email in future. So for today it is all. Thanks for your attention, and bye-bye. Yes, so we have one question. Yes. Yes. Okay, so some questions I have seen now. I will go through all how they came. Here is one question from Mr. Varga. Can we go back to page 10? Yes, of course, I will go to that page. I will not scroll it like a small child. I will try to... No matter. PPTX makes its own life sometimes. Yes, so now we have it here. Yes, we are here. If you only wanted to see this page, here we have it. I can also again say that all this will be downloadable or visible on YouTube by YouTube, but it will be on our web page, of course, on our video system. And if you want to ask something more about it, you can say it now. I will try to look at the bottom. Yeah, there is something unclear. There is mentioned some effect with wave soldering. Yes. Yes, it is. Yes, it is a mistake. Yes, it had to be reflow soldering. Yes, sorry, it is just a translation mistake. It had to be. It simply had to be tento. Yes, yes, as you write, it is caused by reflow solder. Of course, it is only a translation problem. Of course, it is in reflow. Yes. Then we have here another question from Mr. Donfield. The values of decoupling capacitors are taken in account of decreasing the value by applying a voltage across them. Yes. Yes. Thanks for this question, and it is the fact which also, as far as I know, many designers even don't know that it exists, that actually the majority of especially ceramic capacitors decrease their capacity when applied a DC voltage on them. So in real life, when you have, for example, quite big ceramic capacitor, let's say 10 microfarads on 10 voltages or 16 voltages, let's say, when you look into datasheet for a given capacitor, you will find very strange and not pleasant fact that the higher voltage applied is the lower the real capacity of the capacitor is, and the dependence is so very high at some materials of capacitors that you can end up with a capacity of, for example, let's say 1/10 or 1/5 of original capacity. So you have two solutions: or to use bigger capacity, taking in mind this fact, this phenomenon, or you simply can also use higher quality capacitors made from other material. For example, X7R is not so extremely dependent like Z5U or similar high capacity materials. And also a very good thing is to use capacitors which are declared for higher voltage. Yes, naturally, when you use a 25 volt voltage capacitor and at 5 volts, you don't push down the capacity so low as in the case of you would use, for example, only a 6 voltage capacitor, which would of course withstand this, but its capacity would drop very much. Yes, and as for capacitors, for the end of our presentation, I will also tell you that the capacitors from real praxis are often underestimated by designers. One could say 10 microfarads is not always 10 microfarads. Yes, it is extremely different whether you will use the cheapest electrolytic capacitor, 10 microfarads, or you will use a low ESR equivalent serial resistance capacitor, or you will use tantalum capacitor, or you will use even ceramic capacitors. Of course, every one of them has its advantages. Sometimes it's only price, sometimes it's property, sometimes it's life. But I would only recommend you to always measure and only, for example, when you have oscilloscope and when you look at the power line by oscilloscope, only then you will see the real influence of a given capacitor in a given circuit. And if you have a fast enough digital oscilloscope which is able to store some transition, some effect which you can analyze later, you can see really very almost invisible voltage drops sometimes. And that's all. For example, just to tell you that really differences between capacitors are very, very high, and many times even the capacitors which are declared to be almost the same from various producers are not quite the same, especially as for small SMP electrolytic capacitors. In this area, you can find many high quality, but also many low quality capacitors. Yes, yes, I see. So also thank you for all who also gave some questions. We have no other questions here. So thanks again for your attention, and see you next time on some of our next webinars. Bye bye.